This is Organic Chemistry 2026, draw sheet 1. Continuing from question 4. Question 4 says, consider 2-methylbutane, which is also known as isopentane, sighting along the C2C3 bond. Draw all Newman projections of isopentane and indicate the dihedral angle for each projection. So we actually also did something similar for the question that's on top there, you can see. Okay, where we also stated the dihedral angles. Now looking at the bond that they've asked us to look at, it's really easy. Okay, when you want to work out these things, the first thing that you just have to make sure you understand is that you have got staggered configurations, and then you have got eclipse configurations. Once you understand that, then that's better. It means that everything else is going to be very, very easy. So first thing first, the molecule we are talking about is 2-methylbutane. So it's like this, carbon is a butane, so meaning it has got 4 carbons, isn't it? Okay, let's see if I've got space down. Okay, there's no space, so I have to fit everything here. So carbon 1, carbon 2, 3, and 4. But it is a 2-methylbutane, meaning that at question number 2 we have got a methyl. So I'm going to label these ones. This is carbon number 2. This is carbon number 3. So let's say we put our eye at this point. You are looking through the bond. Okay, like that. That's what it's saying, sighting along the C2C3 bond. So carbon number 2 is going to be the front carbon. And then carbon number 3 is going to be the carbon at the back. Okay. One thing that I want you to realize is that this guy, I can also write it like this. Carbon number 2 is bonded to a methyl on top, that is CH3. It's also going to be bonded to an hydrogen that you can see is bonded to also a methyl here. So let's say this is a CH3 and then another hydrogen, okay, that you can see. And then carbon number 2 is bonded to carbon number 3. Carbon number 3 has got one methyl, which you can see here. So I can write that like this, CH3, then it's bonded to hydrogen, and then to hydrogen. So this is the molecule that we want to draw. Okay. So the possible structures that we are going to be able to draw. The first one, carbon number 2 is this carbon in front. I'll write it like this. Okay, you can see that's a dot representing carbon number 2. Carbon number 2 has got a methyl Z and a hydrogen. Let's say, let me put the hydrogen on top, and then the methyls, I'll put them like this. I'll put one methyl this side, I'll put another one this side. And then you have got the carbon number 3, that's the carbon at the back. I'll write it like so. So for the carbon at the back, I'll start with what we call the eclipse configuration. Okay. So for the eclipse configuration, we can have one hydrogen eclipsing. Okay. That's the hydrogen eclipsing with the other hydrogen. And then remember this carbon here contains two hydrogens and a methyl. One hydrogen will eclipse with this hydrogen, one methyl will eclipse with the other methyl. So this is the eclipse configuration. We can start with this one. This is eclipse. And let me start for this one, the bond angle theta, going to set 0 degrees because we don't have any angle between the atoms, this eclipse. And then we'll start rotating these molecules. Okay, we'll be rotating them. So for the second molecule, the carbon that is in front, I'll still write it the same way it is. We have hydrogen on top, a methyl down, and then a methyl this side. And then we have got the carbon that is at the back. Now the carbon that is at the back, what I'm gonna do is I'm gonna rotate it. Okay, so if I make a rotation, what you are going to see is that you can see this hydrogen that is in red. Every rotation that you make, things move by 60 degrees. So this hydrogen in red will move by 60 degrees. It will come on the middle. It's now here. And then we have got this CH3 that we can see here in red. It will now come here. This hydrogen that you can see, it will now come here. So in this case, the angle between these atoms is 60 degrees, and this is known as the staggered configuration. Okay, that's a staggered configuration. And specifically, we can actually call this type of staggered, this is actually a gauge. Why gauge? Every time you have got CH3 next to CH3, we call that as a gauge. Okay, so in this case, the bond angle between the atoms is going to be 60 degrees. I've mentioned that this is also known as a gauge. Every time you have got CH3 next to CH3, we'll make another rotation, another 60-degree rotation. The carbon in front will still be the same. We have got hydrogen on top. We have got a CH3 here, and then a CH3 here. But the carbon that is at the back, what will now happen is this hydrogen that is here is now going to find itself here. This CH3 which is here will now find itself here. And then this hydrogen here will now find itself here. This is another eclipse configuration. Okay. But now I will, from 60 degrees, we've done another 60-degree rotation. So this is 120 degrees. We'll do another rotation until we reach 360 degrees. So another rotation. The carbon that is in front is not changing. Hydrogen there, CH3 here, CH3 here. The one at the back now, this CH3 that we can see here will now come here. And then this hydrogen that you can see in red with the CH3 will now come here. The hydrogen again here will now go there. This is still a staggered configuration, and it's still gauge because we have got this CH3 is being next to each other. But now we have done another 60-degree rotation, so this is now at 180 degrees. We'll do another rotation. The carbon in front will still be there. This is hydrogen, and then this is CH3. This is CH3. The carbon that is at the back now, that's the one in red. This CH3 that is here is now going to come here. This hydrogen will now come there. And then this hydrogen will now come here. This is another 60-degree rotation. So 180 plus 60. This one is an eclipse configuration. Okay. Another 60-degree rotation from 180. That is going to be a 240 degrees. We'll do another 60-degree rotation. The hydrogen in front is still the same there. CH3 here, and then CH3 here. The carbon at the back, I said hydrogen, but I was supposed to say carbon. So this CH3 that you can see eclipsing will now come here. That is a CH3. And then this hydrogen here is now going to go there. And then this hydrogen on top will come here. So this one is another staggered. It is still called a gauge. Why are we calling it a gauge? because you can see really the bond, the CH3s. Okay, you have got CH3s uh, between these atoms. Okay, so let me even put gout so that you can see these CH3s, even these ones, they'll be repelling each other. That's what we call a gouge. So the bond angle now is at what? So that 240 plus 60, that is a 300. And then we are remaining with the last structure, another rotation. The carbon here in front will still be the same, hydrogen on top, CH3 here, and then CH3 here. And then the carbon at the back, another rotation. Okay, so this is CH3 that is down, will come and eclipse with the CH3 this side, the hydrogen on top, on the corner will eclipse, this hydrogen also will eclipse. So this is an eclipse configuration, and we the bond angle here is 360 degrees. One thing that I want you to realize is you have got some special staggered configuration. So for the staggered configuration where I've got the two methyl groups being on opposite sides, we call that as an anti. Okay. For example, you can see this CH3 and this CH3, they are on opposite sides. We call this as the anti configuration. It's a type of staggered configuration. And that's the same one with this one. Okay. That's AND. And the AND configurations are actually the most stable structures because the bulk groups are on opposite sides. But it's tricky for this kind of structure because even if it is AND, you still have gauge here. So that will still make the molecule unstable. So draw all Newman projections of isopentene and indicate the dihedral angles for each. So we have just done that. Okay. The next question is saying plot a labeled qualitative graph potential energy versus rotation for the C2 C3 bond in isopentane. So now on our graph, we are going to have our y-axis and then our x-axis. So you need to realize for those structures that we've drawn, you need to know the most stable structures and then the unstable ones. Okay. So the x-axis is going to be having the rotation. That's basically the angle. And then the y-axis is the energy. That's the potential energy by each bond. When you look at the angles, we are starting, of course, at 0 degrees. We are going all the way to 360 degrees. Half of 360. Okay, we are moving in 60s, isn't it? Okay. How many 60s are in 360? That is 6, right? So divide here. Hope that's the middle. Okay. And on that middle, how many 60s are in 180? So this is 180. Okay. There are three, isn't it? 60s, there are three of them. So divide this here, here and here. Hope that's all equal. Here and here also. So that this can be 60. 60 plus 60, 120. 120 plus 60, 180. 180 plus 60, 240. 240 plus 60, 300. 300 plus 60, 360. Okay. The most unstable structure is the eclipse configuration. So go to the eclipse configurations. And the most unstable eclipse is where I've got CH3 is eclipsing. So when you look at one, the first structure is eclipsed, okay? And then the last structure is also eclipsed. The third one is also eclipsed. The fifth one is also eclipse. So here, the third structure, okay, sorry, the first structure, you can see an eclipse between CH3 and CH3, and then the others are just hydrogens. Even the last one, CH3 and CH3, okay, the others are hydrogens. Even the last one, CH3 and CH3, the others are hydrogens. What does that tell you? It means that these three structures basically have got the same energy because it's the same bonds that are eclipsing. So at 0, 240, and 360, we have got the same energy. Okay, and that's the highest energy because it's the energy of instability. So at 0, that will be on top. The next one I said what is at 240. 240 is here, and at 360, that's also here. And then let's now go to this. So that's the highest energy. Okay, it is on its own level. Sometimes they'll give you the energies for you to calculate. Okay, they'll give you the Gauch interactions between the CH3 and the CH3. Let's say if they say that the Gauch between hydrogen and the CH3 is 2, and then the Gauch between CH3 and CH3 is a 4. So meaning that this is going to be 4 plus 4 plus 2 plus 2. Usually the Gauch between hydrogen and hydrogen is a 0. So you add up those, that will give you the energy of instability. We call that as the steric strain. Okay, it's the energy that is keeping these molecules unstable. So the most stable structure I said, remember, is the ant. And at 60 degrees and at 180 degrees, we have got ant configurations. So those are the most stable. Generally, staggered configurations are more stable than eclipse. But even for the staggered ones, the ant is more stable than any other staggered. Okay, so at 60 and at 180, those are very stable. At 60 and 180, those are actually the most stable. So the energy is going to be very, very low here and also here. That is at 60, isn't it? At 60 and at 180. And then which other staggered has remained? It is the one at 300. It is staggered, but you can see these three groups are next to each other. So that makes this molecule, even if it is stable, to be more unstable than the other ones. Because you can see for the second one, you only have this methyl being next to this methyl. Okay, only two of them. So meaning that that's the only gauge you have. But for the others, like this one, the gauge is nearly throughout. So that makes this molecule to be really, really unstable. Okay, hope you get that. So the most unstable is actually at 300. Or it's not really the most unstable. It is stable, but it's not as stable as the one as Kistan at 180. So at 300, the energy is going to be a bit higher, but it's not as high. So this is how the structure is going to be moving. So this one is going down, okay, like this. Oh, I have not even put at 120 degrees. So at 120, that is an eclipse also. So the energy is also on top. So it is also here. So it's going to be like that. It's going to go up, and then it will come down, go up again, and then come like that, and then like that. So the most stable is the structure that we have just drawn at 180. Okay. Oh, not at 180, but at 300 degrees. Right. Do we have any question of what we've done here? Any question? Okay, I believe that's okay. Please make sure that you understand how to be able to come up with this diagram. Let me look at the energies again. We have got the eclipsed. The eclipsed, all of them are going to have basically the same energy. Okay, this is CH3. Let's look at this again. This is CH3. This is CH3 with an hydrogen. This is just hydrogen, hydrogen. That's for that eclipse. And then this is CH3 with an hydrogen, CH3 with an hydrogen, CH3 with an hydrogen. Okay, for the eclipse ones, the energy is not going to be the same. I didn't pay I didn't pay particular attention to that. I thought they are all eclipsing equally, but it's different. Okay, it's different. The most unstable eclipse are those where the CH3s are eclipsing. The first one, you have got eclipse between CH3 and CH3, and then CH3 and H, and then then H and H. For the third one, it is CH3 with H, CH3 with H, CH3 with H. You don't have any CH3 with another CH3. So meaning that the first one is very, very unstable. Okay. Number one is very, very unstable in comparison to number three. And then if you look at number four, it is between CH3 and H, CH3 and CH3, H and H. Okay. So for this one is number five, is actually similar to number one. Okay, so this one they have got similar energies. So at 0 and at 240, the energy is basically the same. So 0 and 240. So I'm gonna put that there and also here. Another eclipse is the one now at 360. You can see that is H with CH3, HH, and then CH3, CH3. Can you see how this one is? CH3, CH3, and then H with CH3, and then HH. So this one is also similar to the others, isn't it? The bonds are the same. That is at 300 and 60. And then you have got the eclipse now, which is at 120. That one is between only hydrogen and CH3. So even if it is unstable, it will not be so unstable. The energy is not going to be as high as the other eclipses. So this one is going to be a bit lower because the repulsions, you don't have any repulsion between CH3 and CH3. It's only between CH3s and hydrogens. So at 120 is going to be a bit lower in comparison to the others. And then we go to the staggered. The staggered we start with the ant, which are the most stable. That is at 60 and 180, like this. And then we're remaining with the one at 300. It's also a staggered, but at least it has got more gauge. So it's going to have a bit higher energy than the other staggered. So it's going to be somewhere here. Okay. So this diagram should move like that. So just connect from the very beginning. Mm, goes like that. And then it is going to go up. And then it goes like that. Okay. So that's how it's going to go. But I want you just to take note. For some, they will start, what they'll give as a reference angle is actually the ant configuration. Okay, the stagger that is in ant, that will be given as a reference angle. Because the thing is that as you are drawing this structure, you want it to come out a symmetrical graph so that you see how it will appear. So you can see the ones that are on the top, which is this one which you have put at 240, and this one which you've put at 360. Let's look at those. At 240, where is it? Okay, this one. So that's why we're going to start as the 0 degrees and then the one at 360. So I just want you to see what would happen if you change the way the angles started. A lot would actually get to change. So if we said that this is going to be our 0 degrees, okay, and then you are doing your rotations. If you do the first rotation, why have I started from this one as the 0 degrees? What's the difference with even the first one that I wrote as 0? These ones are basically the same, isn't it? The one which is at 0 and the one, let me see the way they are appearing on the graph. Yeah, they are basically the same. But then the energies will actually be a bit different on the structures that we are going to draw if the graph is going to come out symmetrical. But for this one, I think just this is okay. Where the angle where we started is fine, so I can just write like that. What I'm just trying to show you is that as you draw some graphs will really come out well. It can start like that, it goes down, and then it comes like this, okay, and then it goes like that. That's just telling you the energies. But we've already labeled everything on our graph, and we know which one is at 0, which one is at 240, which one is at what angle. Okay, so that's how you draw this structure. Number 5 is saying, I hope we are okay. I've really taken some good time on explaining this question. Number 5 is saying, show by calculation using the formula delta G is equal to negative RT natural log of K that free energy difference of 7.3 kilojoules per mole between the axial and equatorial forms of methyl cyclohexane at 25 degrees Celsius does correlate with the equilibrium mixture. Okay, let's draw first the structure methyl cyclohexane. Remember, it's a cyclohexane. We want to draw a chair. So for a chair, the first thing that you do, draw two parallel lines like that, and then connect these lines. Okay, I left starting the lines like so. You can start in any direction you want. These are two parallel lines. Just put a dot on top here, put a dot down here, then just connect them. Okay, like that. And then we are going to flip this chair. The flip just means pull this carbon down, pull this carbon on top. So we'll now draw parallel lines going in this direction. And then I'll put a dot here and then a dot there and then connect them. Okay, like that. Now, remember, we have got a methyl. This is a methyl cyclohexane. So you're going to decide yourself where the methyl is going to be. Please decide yourself. Let's say this is carbon number 1 here. If the methyl is facing upwards, and it's up to you to decide where it's going to face. So if it's facing upward here, it is in the axial direction. Axial is basically up. If you flip the chair, because what happens here is that this is carbon 1, number 2, number 3, 4, 5, 6. In case you don't know how to draw chairs, I've posted it. We did the class and this on the drive, you should know how to write. So if you flip the chair, carbon number 1 will now be this one down because you simply moved carbon 1 down, carbon number 4 has been taken on top. This will be 1, this will be 2, this will be 3, 4, 5, and 6. So what happens is that after flipping the chair, what was in the axial will go equatorial. Okay, but remember the methyl was axial up, so it will be equatorial, but it will still be up. So it will be like this. So after a flip, you maintain the position. What it only differs is if I'm writing the cis structure and the trans. Cis means that the two groups are in the same direction. For example, this and this. These two guys are in this. These structures are cis. Okay, because they're all facing up. Or let's say we have got a Matthew like that, then we have got another Matthew here. These are cis because they're both facing up. If it is trans, one would have been facing down, the other one is facing up. So for cis and trans, you look at the direction. You don't look at equatorial and axial. Okay. Now you need to know that for the group or the structure which has got a bulk group in the axial, that's the most unstable structure. So this one will write a longer arrow going towards this guy this side and a shorter arrow in this direction. Why? Because this structure is more stable. Majority of the times, methylcyclohexane will find itself in this form where the bulk group is in the axial direction. Okay, because it's very stable. Why is it that this second one, where I'm saying the bulk group is in the axial, so I'm going to say this is axial, and then I'll say this is equatorial. Okay, this is actually because the arrow is pointing more to the forward to the axial. We'll say this is the product because majority of the times our compound wants to be in that state. I'll say this is the reactant because it is actually the most unstable. Okay. The reason as to why the one I've written as reactant is very unstable is because of what we call 1,3 diaxial interactions. So what will happen is that the methyl that is in the axial will move 3 steps in both directions. So from here, from where the methyl is, 1, 2, 3. So there's an hydrogen here. And then from where the methyl is, 1, 2, 3, there's an hydrogen in the axial direction. So there'll be these interactions. We call them the 1,3 diaxial interactions. And those are the ones that make the molecule that is in the axial to be very, very unstable. Okay, in comparison to the other molecule. So that is what happens. The 1,3 diaxial interactions, we'll show them using dotted lines. Okay, so that is the first thing. So if you know the energy of the guy that is in the equatorial and then the energy of the guy that is in the axial, you can actually calculate the change in energy between the two molecules. You can calculate the change in energy between the two molecules. How can you calculate the change in energy? How do you calculate change really? Change in energy. Change in energy is given just by product, okay, minus reactant. But there's also another equation given there that is a Gibbs free energy. Okay. But before then, because this reaction is actually finding itself at equilibrium, we can calculate the equilibrium constant. Okay. The equilibrium constant K is given by the energy on the product divided by, and you know this is how we always find K. It's product divided by reactant from our chemistry, isn't it? Okay. And this is going to give us K being equal to, remember the product is the structure that is in the axial, reactant is the equatorial. So this will give us A being equal to K multiplied by E. That is just a simple equation that we need to know. Okay. Now let's go to the delta G equation so that we just calculate the value for K so that we can use it. So to calculate the value for K, we are gonna say delta G is equal to negative RT natural log of K. Now delta G is basically the energy difference between the product and the reactant. So how we find delta G is we simply say product, which is the A, minus the energy of the reactant, which is E. Okay? And we've already been given that the free energy difference is 7.3. Now you need to know that this free energy difference, because we get the one that is stable, look at this. The one that is stable is going to have little energy because it's stable. Little energy means that it has got little steric hindrance. So it's going to be, let's say, 4 kilojoules. And then the one on the reactant is the one which has got high energy. That is the energy of instability, maybe 8. So it is 4 minus 8. So the answer for delta G is always negative. But when we are writing it, we only give you a positive value because we assume that you already know. So they've said that the free energy difference of 7.3 kilojoules per mole exists between the equatorial and the axial. So that 7.3 kilojoules is actually negative 7.3 kilojoules per mole. And remember, it is kilojoules. Okay, so delta G is negative 7.3 kilojoules per mole. When we are using equations, we don't deal with kilojoules. So multiply by 1,000. So this is 7,300 joules per mole. Okay, so that's the one we put here, negative 7,300. And then we have got R. The invisible gas constant is a constant, it's 8.314. 8.314. The temperature we are told is 25 degrees. This should be in radians. That is 298 kelvins. In case you want, put 0.15 because 298 is the same as 298.15. Okay, let me put there 0.15 for the sake of my calculations. 298.15, the natural log of K. At this particular time, what you do is you are going to simply divide through so that you just remain with natural log of K. So divide this side by negative 8.314 and then 298.15. Also this side negative 8.314 and then 298.15. So that will leave us with natural log of K being equal to, that is gonna be 2.945. Now natural log, this is mathematics. Natural log of K just means that you have got a log in base E of K. Okay, this is the mathematics which you did at first year. And we know for you to convert from a logarithm to to an exponential function, the K here is going to be the number, and then E is the base. And then the answer here, which is 2.945, is going to be the power. So the way you punch this on your calculator is just go on shift, you go on where it is written natural log on your calculator, that's where E is. So just punch shift, you press on natural log, E will show. And then just type 2.945. Don't put power 2.945. If the E is showing on your calculator just right now, 2.945. Okay, and then say answer. That is gonna give you 19.01. 19.01. Okay. Now that we have found this value, I want you to realize this. If the amount of equatorial is 10, just know that the amount of axial is going to be 90. If you add equatorial plus axial, it should give you 100%. So if we are working with decimals, okay, if you are working with decimals, amount of equatorial plus amount of axial must be equal to 1. That one is in terms of decimals. Okay, that's what I want you to know. And I told you earlier that this is the equation here. K is equal to A over E. And we said that A is equal to KE. So what are we gonna do? I can make this same equation here. One of these guys is subject to the formula. Okay. So I can just say, let's make E the subject to the formula. So E is going to be 1. We'll take A the other side, minus A. And then I will bring the equation that we derived earlier to say this one. Okay? To say A is equal to KE. and we'll say A is going to be equal to, where there is K, all right, we are going to substitute 19.01. Where there is E, we'll put 1 minus A, and this is going to give us A being equal to 19.01 minus 19.01A. We'll take the 19.01A the other side, so it will be A plus 19.01A being equal to 19.01. A plus 19.01A, that is gonna be 20.01A being equal to 19.01. So therefore A is going to be equal to, we'll now divide 19.01 over 20.01. 19.01 divided by 20.01, that has given me a 0.95, okay, 0. So if this is the amount of A, we can determine the amount of E. So say therefore E is going to be 1 minus 0.95. So that is 1 minus 0.5. So that gives us E being equal to 0.049975. So in conclusion, we are going to say therefore the amount that is in the axial is going to be, that 0.95 is a decimal, convert it to a percentage, multiply by 100. That is 95% is in the axial, and then in the equatorial, that is 0.499 multiplied by 100. That is gonna be 4.9975%. As you can see, majority of this substance is actually in the axial, because the axial is a stable form. That's why you are going to find majority of the substance in the axial. Okay, so the question was, show by calculation using the formula delta G is equal to negative RT natural log of K, that a free energy difference of that between the axial and the equatorial forms of methylcyclohexane at 25 degrees does correlate with the equilibrium mixture, in which the concentration of the equatorial form is actually 95. Okay. What has happened here? This is saying the equatorial form is actually 95. Oh, sorry. So the equatorial, I just swapped this again. The most stable form is the equatorial, not the axial is this one that I said it's very, very unstable. Okay, because of the 1,3 diaxial interactions. I even mentioned the 1,3 diaxial interactions. I wonder why I put that as the equatorial. Okay. So this guy is actually going to be going in the backward direction. So the most stable structure is actually the one in the equatorial. Okay. So this me taking me back, really take us far. Okay, let me just make the few changes just here. Okay, I'm going to write it the same way I've written it, and then I'll just say these letters representing this. This will be still equatorial. Okay. And I already said that the stable one is actually the axial. Please take note of the equatorial. Okay. The one that I said A, I'm going to say A is representing equatorial, but it's not supposed to be like this. Okay, E is supposed to be representing equatorial, and then I'll say E is representing the axial because I just made a mistake on the letters. I hope you get it. Okay, and then number 6 is saying draw a stable chair conformer for CC 1,3 diisopropyl cyclohexane. Draw a stable. You hear the language? It is a stable. When you are drawing how many structures? One structure. Okay. The first thing that I want you to know is basically the structure. So it is a cyclohexane. So write the cyclohexane. 1, 2, 3, 4, 5, 6. 6 cyclohexane. So it is 1,3 diisopropyl. So at position number 1, let's say this is position number 1, we have got isopropyl. Isopropyl is like this. Question number 3 also have isopropyl is also like that. Okay, that's the one. Now the stable one, you need to know that the stable one is actually the structure where you're going to have these bulk groups. Okay, when can you have a stable one? Stable must be where the bulk groups are actually in the equatorial. Because if they're in the axial, they are going to form what we call the 1,3 diaxial interactions, and that to make the molecule so unstable. So the stable structure is the one which is in the equatorial. Okay, so we'll do like that, two parallel lines, and then put. I still love starting with lines that are going like this. Put a dot there. Put a dot there. Connect. Okay, like that. So we again have to decide which one is gonna be carbon number one. Okay, which one is gonna be carbon number one. So let's label it, and then we'll follow. This will be one, this will be two, this will be three, 4, 5, and 6. So carbon number one is the one we are going to put the atoms in the equatorial, not the axial. So carbon number one will put our group in the equatorial. Is going to be equatorial goes down. Okay, so that's our group there. Position number 3, we also put in the equatorial. So equatorial here, because here the axis is going to be going up, the equatorial goes like this. So this will be our molecule. That's how you get to draw a chair conformer. I hope this is okay. Okay. So both groups are in the equatorial, so this is the stable structure. If one of them was in the axial, because we can draw 4 possible structures where one group is in the axial, the other one is in the equatorial, we swap them. The other which was in the equatorial goes in the axial, the one which was in the axial goes equatorial, or both in the axial or both in the equatorial. You can try out to write the other structures that I've not drawn there. Okay, so this is the most stable. Both groups, they are equatorial. Okay, and then we have got the last question, question 7. Consider one bromopentane sighting through the C1C2 bond. Construct a Newman projection for ANT, gauge, and two eclipsed configurations. Okay, for ANT, for gauge, and two eclipse. Remember, this is one bromopentane. So, sorry, one bromopropane. Propane is 3 carbons. One, two, three. But at carbon number 1, there's a bromide. So I can put a bromine here like this. Even if you can't see, there's an hydrogen here and then an hydrogen. This is carbon number 1. Carbon number 2, besides it having this methyl, It's also going to have two hydrogens. Okay, this is the molecule. So we want to draw Newman projections for anti, Gauchi, and 2 eclipse. So let's start with the ant. We'll just start drawing the carbon that is in front. That's carbon number 1, which is this one. This is carbon number 2. So carbon number 1 has got a Br on top, and then there's a hydrogen here, and then a hydrogen there. And then we'll now put the carbon number 2. The first structure that we are drawing is the ant. So the methyl should be on the opposite side. And then the hydrogens will be here and here. So this is the ant. And then we'll draw gouge. Gouge means that the CH3 and the Br are actually next to each other. So I'll still draw the same way this is. Br on top, hydrogen here, hydrogen here. Then we're now going to have the carbon that is at the back. We can have the CH3 here, and then one hydrogen will be here, one hydrogen is here. This is a staggered configuration, specifically we call it gauge. Okay, so as I was saying, this is a staggered configuration, but we specifically call it gauge because the two groups are next to each other. This is what we call gauge. And then this group and this group on opposite sides, that's the ant. And then we draw two eclipsed. So we're going to have one. We still have CH3 on top, hydrogen here, and then hydrogen here. And then another one, still have CH3 on top, and then hydrogen here, and then hydrogen here. So we can have an eclipse where the Br is here. Okay, if the Br is here, here will be the hydrogen, the other hydrogen will be here. Another eclipse, the Br can eclipse with the hydrogen, and then the other hydrogens will be there. Okay, so this is an eclipse. It's actually even much more unstable than this other eclipse because it has got the two back groups eclipsing. Okay, so when you are looking at instability, this one is more, let me just label them for you when it comes to stability so that you can just see. This is most stable, and then this is least stable. This one with a gauche is stable. Okay, this one is not really stable, but is stable. Okay, so like that. The last question here is saying, using the information below and the fact that the barrier to rotation, the energy difference between the highest and the lowest energy conformer in 1 propane is 21 kilojoules per mole, determine the contribution of CH3 Br eclipsing interaction. So we want to calculate the value of X here. Okay, that's a contribution. And that's, remember, for an eclipsing. And we've been told that using the information below and the fact that the barrier to rotation, the energy difference between the highest and the lowest energy conformer in 1 is 21. The highest and the lowest is that. So let's start with the highest energy conformer diagram. Highest energy So the highest energy diagram here is the least stable. Okay, so that is least stable. What are the energies that it has? So number one, there is an eclipse. Where is the most unstable? Oh, I actually even swapped these ones. Let me change this BR. I'll change with these ones. The one that is most unstable is where the BR is eclipsing with the methyl. Okay, where it is hydrogen, that one is not the most unstable. Okay, so for the least stable, we have got the eclipse between Br and CH3. Okay, that's the first energy. So eclipse Br CH3 plus, that's not the only energy. We have got also eclipse between H and then H and H again. So we're going to just say plus 2 eclipse between what? Hydrogen and another hydrogen. So this is going to give us the eclipse between Br and CH3 is what we want to calculate. So that is just the X. Okay, yeah, that's the energy cost. And then plus 2, the eclipse between H and H. You go on the diagram, you can see that is a 4. So this is going to give us what? 80 plus X. And then let's go to the one with the lowest energy. So lowest energy is which structure is definitely the one in the ant. Okay. And for the one in the ant, you can even see a gauge between hydrogen and hydrogen is 0 because gauge between hydrogen is actually very stable. It doesn't even have any energy. So for this one, the only energies we are going to have is this gauge between hydrogen and Br, even this one, so there are the two of them, and then the gauge between hydrogen and CH3, and then the gauge between hydrogen and CH3. So I've got two gauge between hydrogen and CH3 and between hydrogen and 2 and Br. So we're going to say 2 gauge, that is hydrogen and CH3, plus 2 gauge between hydrogen and Br. So this is going to be 2. The hydrogen and CH3 gauge, the energy is this side. That is a 1.8. And then the energy between hydrogen and Br, which is gauge, that is a 0.5. Okay. And so this is gonna give us, let's multiply this. So we have got 2 multiplied by 1.8 plus 2 multiplied by 0.5, and that is a 4.6. Remember, this energy is actually in kilojoules per mole. That's also the same way with this one that's written on top. That energy is in kilojoules per mole. Just as I told you on chairs, remember the product is always the stable structure. Remember that? The product is always the stable structure. Okay, I hope that makes sense. So we'll then say, using the information and the fact that a barrier to rotation between the two, uh, so that is the energy difference between the highest and the lowest. So they've even given you that. So barrier to rotation, we'll write that. So barrier to rotation is basically the energy difference between highest minus lowest. And they already gave us the value for the Barrett rotation, and that is the 21 kilojoules. So that is going to be 21 is equal to highest is 8 plus x minus lowest is 4.6. If I want to remain with x, I'll take 8.8 the other side. I'll take the 4.6 the other side, it becomes positive. So x therefore is going to become 21 minus 8 plus 4.6, that is 17.6. 17.6. Okay, so that is that. So the energy is really high. So therefore the CH3 to Br eclipse is equal to 17.6 kilojoules per mole. That is how you get to work out this question. In case you have further questions that you'd really love to find out about, feel free to text me on WhatsApp.